Welcome to Automated Visual Software Analytics. This part is about object-oriented metrics. In this part, we will define object-oriented metrics in general, and we will introduce two specific object-oriented metric sets, the CK metrics and the mood and Q-mood metrics. Let's start with a general look on object orientation. Object-oriented analysis and design are widely adopted in software development and in software industry. The implementation of object-oriented systems is supported by a number of object-oriented programming languages, for example C#, C++, Java, most common ones, and object-oriented modeling languages, for example the Unified Modeling Language UML. The underlying object-oriented design principles include encapsulation, information hiding, and inheritance. These principles aim at, in general, a better management of system complexity and of system evolution. Object-oriented development in general offers many advantages regarding different aspects of software quality and tasks in software engineering. For example, software maintainability, software reusability, or software re-engineering. Object-oriented development, however, requires additional object-oriented specific metrics compared to traditional functional decomposition and data flow-based approaches. These specific metrics for object-oriented design aspects should reflect quality aspects of exactly the object-oriented design. Let's have a look on these specific aspects. Object-oriented software metrics in general are concerned with the following elements of an object-oriented design. This is actually a meta model for object-oriented metrics. Object-oriented metrics investigate classes, their attributes, their methods, how these methods and attributes are accessed or invocated, that is, how these attributes and methods are used. And object-oriented metrics also investigate the inheritance relationships among a class hierarchy. So these are the key aspects object-oriented metrics are interested in. The general objectives of object-oriented metrics include to facilitate, to monitor object-oriented principles in design and implementation, and to support stakeholders in achieving a better consistent object-oriented design. Another objective includes that object-oriented metrics can be used to predict efforts related to, for example, fault proneness, reliability, maintenance and testing efforts for object-oriented systems. Another objective is object-oriented metrics evaluate methods, attributes, classes, their coupling and the inheritance relationships. Let's start with a concrete object-oriented metric set called CK. It comes from the original authors, Kai Damber and Kammerer, was also called MOSI, Metrics for Object-Oriented Software Engineering. This metric set includes a number of particular metrics. Among them are weighted methods per class, depth of inheritance tree, number of children, coupling between objects, response for a class, lack of cohesion in methods. CK metrics measure design complexity in relation to impact on external quality attributes such as maintainability, reusability, and CK metrics are both theoretically and empirically validated. That is, the CK metric set turned out to be a very realistic way of measuring object-oriented design characteristics. To give you one example, I want to explain the lack of cohesion in methods. This matrix assumes that for a given class we have a set of methods M, including the methods M1 to MM, and that the class is defined by a set of attributes A1 to AA. So these are the constituting elements of the class. The lack of cohesion method defines now one function, mu AK, and this function returns for a given attribute the number of methods of the class that actually access this specific attribute. And the lack of cohesion in methods metric is defined now by a ratio between the number of methods that use the individual attributes in comparison to the number of methods. That means, assuming that at least each attribute is accessed by at least one method, that we have a value towards 0 if only one method per attribute uses that attribute, in the average case, and we get a lack of cohesion in methods value of 1. This is a kind of undesired situation if all methods would access almost every attribute. So this measure somehow reflects how methods access attributes within one class in the average case. To illustrate this further, let's have a look on a concrete example. We have 3 classes, but in this example we investigate the LCOM metric value for the rectangle class. The rectangle class defines 8 methods, and it has 2 attributes, position and extent, expressed by 2 objects of type vector 2D. And if we would like to compute now the LCOM metric value for this object-oriented model for the class rectangle, we just put in the values and, most important, attribute 1, the position, is accessed by 4 methods, and attribute 2, extent, is accessed by 5 methods. So if we evaluate this formula, we get an average value of lack of cohesion in methods of 0.5, which is a good value, which is not an extreme value. So in general, this seems to be okay. Of course, it could be improved by applying a certain redesign to this object-oriented model in the future. Yes, this gives an indication about how LCOM values can be computed. Applications of the CK metrics in software analytics include, for example, in the first case, the CK metrics appears to be useful to predict class fault proneness during the early phases of the software development life cycle. Another application includes that higher values of the coupling and cohesion in the CK metrics were associated with reduced productivity and increased rework design effort. There's also a study that a medium-sized telecommunication system appears to have a relationship to the depth of inheritance tree, a number of child aspects or values of this metric. They were found to influence defect density. These are 3 examples of how the CK metrics is used to evaluate certain quality aspects of object-oriented systems, and these results are typical for empirical software engineering. Let's go on to the second object-oriented metric set I would like to present. It's MOOD and QMOOD. It's the abbreviation for metrics for object-oriented design. Typically it's used on a system level, so it's used for the system-wide measurement. Each metric in this system is a quotient of the use of a particular mechanism in the system being measured. This will be the numerator, and the maximum possible use of the same mechanism. It's used as a denominator. The metrics of this set include the method hiding factor, attribute hiding factor, method inheritance factor, attribute inheritance factor, a polymorphism factor, and a coupling factor. So the first metrics refer to the information hiding aspect of an object-oriented design, and the other one to the coupling inside a class and the use of inheritance in an object-oriented design. To illustrate these individual particular metrics further, here are just some statements about the interpretation of their values. For example, if all methods are private, method hiding factor would be 100%. If all methods are public, hiding factor would be 0%. The same for attributes, the same for the method inheritance factor. If there is no reusability, the inheritance factor is 0%. The same for attributes. Interestingly, in polymorphism, if all methods are overwritten in all derived classes, then this factor would be 100%. Of course, in reality, these 0 or 100% are rarely reached, because typically in an object-oriented design, the values are somehow in between. But these values reflect how the particular metrics of mood can be interpreted, and we can even go further and look at, for example, a collection of similar software systems, and we can ask, how do these software systems use different object-oriented design principles? With the mood metrics, we can evaluate these characteristics. For example, here it's an example for systems, Microsoft Foundation classes, the GNU User Interface Toolkit, and ETA Plus and Motif. Give you just one example. Polymorphism is highly used in Motif, whereas it's rarely used in Microsoft Foundation classes. So if we would ask, how could these systems improve, we possibly would recommend that Microsoft Foundation classes could increase the inheritance principle that object orientation offers to take advantage of that principle. Yeah, if we go on to QMood, we can even go further into into quality aspects of object-oriented design. In QMood, we define a number of derived design metrics that inspect the individual consistency and composition of classes. For example, the NOM metric counts the number of methods, or the NOH metric counts the number of independent class hierarchies in a whole system, etc. So based on these individual derived design metrics, we can relate these metrics to certain desired design properties, for example, to abstraction, encapsulation, coupling, cohesion, inheritance, etc. And based on these particular derived design metrics, we can now go one step further to build really high-level metrics for quality, for general quality attributes of an object-oriented system. For example, reusability, flexibility, or the understandability of a system, the functionality, extensibility, or even the effectiveness. And these high-level quality attributes are now measured by taking into account the more particular metrics and weighting them. These weights always sum to 1. For example, reusability was found to be best estimated by taking into account the coupling quality, cohesion quality, messaging quality, and design size. Yeah, with respect to these high-level qualities, we have to say that high-level qualities as shown in this column, yeah, are hardly to express by sharp numbers, but with the object-oriented metric set, at least we can estimate a general indication about their quality status. Let's summarize this part about object-oriented metrics. Object-oriented metrics allow for monitoring key characteristics of object-oriented design in a software system's implementation. Object-oriented metrics are based on a static analysis of the source code, and during that analysis we analyze class features within a given system, and all these tasks for analysis can be done automatically, so can be even done in a fast and robust way. The CK metrics as well as the mood-QMood metric set represent two approaches for object-oriented metrics. Both are used in practice in a number of studies and have been validated in a number of studies. It is shown that these metrics generally facilitate control and monitoring of software quality related to the object-oriented design, and the application of object-oriented design principles in a given software system. Object-oriented metrics represent a key source of information about the object-oriented aspects of a complex, long-term software system. For that reason, software analytics likes to measure and to monitor object-oriented metrics, in order to provide key performance indicators regarding the high-level quality aspects of a system, such as reusability, flexibility, understandability, functionality, extendability, and effectiveness. Now, this concludes this part. Let's see which terminology was introduced. We introduced object-oriented metric. It is defined as an object-oriented metric as a software metric that reflects object-oriented design characteristics of object-oriented systems. We have also introduced the CK metrics. CK metrics are a set of object-oriented metrics capturing concepts of inheritance, coupling, and cohesion in object-oriented systems. And QMood, the quality model for object-oriented design metrics, again is a set of object-oriented metrics capturing the same aspects of the object-oriented system. As further reading, I would like to recommend the following two papers. One is entitled Empirical Analysis of CK Metrics for Object-Oriented Design Complexity and the Implications for Software Defects. The other recommended paper is about mood and QMood, review of mood and QMood metric sets. Both can give you further information about the background and sometimes about, to a certain degree, about the empirical validation and related studies that are behind the development of these object-oriented metrics. Let's end with some remarks. If object orientation is used in design and implementation of a software system, of a possibly large and long-term software system, object-oriented metrics should always be monitored over time because they are a key software quality, and we can check these key software qualities by measuring object-oriented metrics. Object-oriented metrics can be compared, on the one hand, among subsystems and individual components of a given software system to see how maybe different developer teams take advantage of different object-oriented design principles. On the other hand, object-oriented metrics can be compared for other similar projects, for example, third-party systems or even competing systems to see how do they take advantage of object-oriented design principles and what about their metric values related to the object-oriented design. In software analytics, we use object-oriented metrics, especially monitored over time, to identify correlations between different object-oriented characteristics and different software qualities, especially software quality changes, or even a correlation between object-oriented design characteristics and software development activities. So software analytics likes to use and to take into account object-oriented metrics, and due to the importance of object orientation for the development of today's systems, object-oriented metrics represent one key source of information about a software system and its development and evolution.